Hello, so today we are gonna record a video and we are going to code a hill climbing algorithm to solve the 8 puzzle problem. So, what's an 8 puzzle? I found this very interesting paper. Steepest and hill climbing algorithms solve cases in puzzle game 8. This is 8 puzzle game, which you don't know if what it is. It's this thing basically. You see, we will get some disordered thing which with one blank line we have to arrange them in a proper order. So we'll try to solve this puzzle, and in artificial intelligence, it's not a very good way to solve this, but we will use a hill climbing algorithm. Now, what a climbing algorithm does is it takes a heuristic function and tries to maximize the or minimize whatever it is the heuristic function accordingly. So that's what we are going to do today. I'm going to try. What they have done here is they have taken the heuristic to be the number of squares in the correct place. There are another ways we could have used Manhattan distance instead, but oh well, we are not doing that. In the paper, they have done the method I have mentioned, number of correct squares. You can see. So this is a very good paper. I will attach the link to this so you guys can see it too. But let's start. I am making this video for myself because I want to see how much I can code. I want to see how I code with the thinking process and stuff. So let's start. So let's make a initial, and I'm using double list because why not? It would be better if you use a single tuple or a list. It will be better data structure. It will be easier. It will reduce the bottleneck of double indexing and stuff. But I am making a easier version here, so I will use the double goal. So the goal variable is 1, 2, 3, 4, 5, 6, 7, 8, 9. So each represents a row, and each list itself represents a row. And by commas, we are representing their different sorry, the opposite. Uh, this is the first column. So this is basically a 2D matrix we have created here. Anyways, those are our initial, that is our goal. Let's make an initial as well. That's not a 9, that's a 0. 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's name it init 1, and let's make an init 2 as well. 1, 2, 3, 4, 5, fuck. 4, 5, 6, 7, 8, 0. Oh, 9 here, it's 0. Let's switch it up. Let's switch this with this. Then we'll switch this with this. And that's our init 1. Init 2 we will see later on. So should we make it right now? Let's make it right now. 5, 8, 0. Let's switch it with 2 as well. And while we are at it, let's switch it with 1 as well. So this is the thing. We have made two initial ones which we will solve using this. So now first function we will make should be to get the index of 0. So def get 0, and we will get the state. So now we will once I demonstrate for in range 3, 4, 3 in range 3 if state of I and j equal to 0, we will return I comma j. Later we will return null comma null. Oh, this is wrong language. None comma none. That's that's how we'll get the zero. Very bottlenecked function of n square. So yeah, but that's what we have to adjust with if we make it easy. Optimizations are a later on process. First get the work done. So now def get zero is done. Now we have to somehow get the heuristic of initial, and we'll pass the goal as well. So for let's put the issue equal to zero for I for row in it. If we do like that, it won't do. So we have to access the index for I in range 3 for G in range 3. You can update it a lot, but let's see afterwards for J in range 3. If init of I J equal to and goal of I J. Wait, yeah. If that's the case, then here plus equal to the 1. Neither we go on until that. Then we will return heuristic. So here we are trying to reduce the heuristic as much as possible. We could have done the opposite and run minus y, but I'm not sitting here calculating the maximum amount of heuristic a function can have, and I don't think it would be fair to start at a random number. We can, but nah. So heuristic is done. We will get the heuristic how we pass. Now I think we have to do get neighbors. So this will give us the new states. This should give us a list of all the states. Is what I'm saying. So we will get neighbors of init, or I will just mark the state directions a list we'll make of it should be up, down, left, right, and we'll make a neighbors list. We'll make, well, you can make it a tuple. Let's make it a tuple. That's what we will insert tuples into it as well. I don't know why we will do that, but I just prefer tuples if you're not actually changing anything there. So now we have to do for direction in directions. If direction equal to up, and oh, also we have to get zero as well. No? A comma j equal to get zero of state. So let's see. If you want to move up, let's do. You cannot move this up. Why? Because there is no element above. So I should be greater than zero. We have to copy the state as well. More equal to, I guess it should work like this. If not, I will open up ChatGPT. Hey, this is fully honestly I'm doing. Rotation will up and equal to 0, then we switch it up. So, board of ij and board of I minus 1j equal to board of I minus 1j and board of ij. And if direction equal to down and I less no, down, it should be less than 3 or 2, less than 2. Then in that case, we will do board of ij, board of I plus 1 j. I hope you understood that from here since if it's more than 2, if it is 2 or more than that, you can do it. So equal to board of I plus 1 j and board of I j. Now I leave direction equal to left, and now we have to check j because now we are moving like this instead of like this, right? So we have to check. We are moving it leftwards. So let's check this condition. Left. Can you move this left? No. Why? Because it's the j is less than it's 0. You can do it with 0. So we have to do j greater than 0. In that case, board of ij and board of ij minus 1 equal to board of ij minus 1 and board ij. Now you can do, but I will just do else because I'm not wasting time. Board of ij. No, you can do else because we have to check the condition. So if you're doing checking the condition, this one here anyways, why not check the direction as well? So I will just write right and j less than 2 board of j board of I j plus 1 equal to board of I j plus 1 and board of I j. So that's how we do it, and then we will just append it into the neighbors dot neighbors dot append, and then we append the board. We just append the board? No, we don't. We have to append a tuple where of board, comma direction. Remember, this will insert, but the problem here is it will check. It will insert normal ones into it too. Like does not match. Like look, this is the state. Agent move is up. First one up. Sees nothing. It cannot change. Nothing else matters. It just appends the normal board with the direction up. It did not move up. So you have to change that. I guess for this reason we have to do it individually everywhere. Okay, and then we will return the neighbors. Great. So we have got the get neighbors as well. Now I think it's time to start the hill climb agenda. Hill climb of initial goal. That's it, right? And if you want to put the heuristic here too, if you have a future, if you want to change it, you can put heuristic there as well. But for now, I'm just doing it normally. So that's our hill climb. Let's start doing it now. So first of all, that's our in it. So for each one, we have to keep track of the best rate. We keep track of the best. The best should be float of. We are trying to reduce it. Remember, so initially press. It should be just a float of infinite. And then comes for. So while true, let's do it while true. The base condition should be if it is equal. If init equal to goal, we just print goal reached and we return. What do you want to return? Do we make a path here? Want to do that? Let's see. Uh, doesn't matter what we return for now, so I will just make path and we'll return path. Actually, yeah, we should return path. Then comes neighbors equal to get neighbors of. Oh, we also have to make a current variable. And then for neighbors in for neighbor in neighbors. So now we will get individual and neighbors returns a tuple like this board and direction. So board neighbor direction in neighbors. This is what you have to do. Does the best go outside or the inside? Is the steepest hill climb rate? This should go inside, I'm guessing. Where true. Let's mark it here. For neighbors, direction in neighbors, getting the both the values. Are we? I hope we are. So neighbor direction in neighbors. Now what we have to do is we have to check if it is less than the value, the best value that is. So since this is the steepest, we will go through everyone and select. So we have to have a best dir as well. Maybe dir equal to 1. If heuristic of neighbor is less than the best, best equal to, instead of really accessing, and just put it as h equal to heuristic of neighbor. Since we don't want to recall the function every time and important make it for our time complexity. So if h less than best equal to, what does best store? That's one thing. Best equal to h. H. How do we keep track of it? Because we have to keep track of the board, which is the best. B board equal to minus best equal to h. B board equal to current. B board equal to current, and then we have to also do meter. Oh, B board is never not current. Then B there. The best direction will be the direction. And after all this, we will get the best neighbor. And once we have got the best neighbor, we will print it out, right? Or we'll add it to path, better path thought. Append, we have made it list, right? So this will be a list of the best board and the best direction. Print. Now, one thing we have to make a function to display board as well, right? Because if we're printing the board here, because we need that for checking. So print board will get a state. What we'll do is we'll print for I. Yes, that should print the board. We'll do print board. What will board print is the B board, and we'll also print wait or F string it and so move better. Yeah, that makes sense. And then we will set the current as the B board. Perfect. I think this should work. पाथ डॉट append भी कर लिया है हमने. Let's see. Now a hill climb off init one, right? Let's see. Fingers crossed. Okay. Oh, I did not give it. Oh, I did not give it goal. Goal. Yes. Tuple object has no other append. What does? Oh fuck! Tuple can't append stuff. Right? Neighbors can. Oh my bad. Yeah, neighbors is that. This is I do such. Oh, oh what? Let's open the try and see the error. 967. Okay. Oh yeah, I have to do. Goal. You also have to do the limit at some point, right? Okay, stop. Why is it going in an infinite loop? Why is it going in an infinite loop? I have set return path here. See, see, this is where you will see me. See, it stopped, it stopped. Several logical and structural issues will go. Oh fuck. I hate it on statement I. For I insert and for statement I. For J and I. That was a silly mistake. You are counting matches. And also, yeah, one more thing. Oh yeah, oh yeah. What did I do? Okay, sorry, sorry. Yeah, it should be greater than. We are trying to maximize it. If it was the we are counting the mismatched ones, in that case is when we have to minimize it. Yeah, I am really sorry for that mistake. I'm really sorry. The better heuristic misplaced is excluding zero. No, I'm fine with the one I'm doing currently. Okay, this is the code. Yeah, I knew I was missing. I knew I was messing up. But let's understand how this is working. Vertical to list of row, not for row instead. Okay. What I did was I was double indexing it somehow, and that was not doing it properly. What it? And it's not init equal to goal. It's current equal to goal. That was again these are silly mistakes which I am doing. These are not major flaws except one syntax. Again, the syntax. These are silly mistakes. In local maximum is not our issue, right? Let's see. What? If current equal to goal. Current is in it. Well, let's see. Just stuck on line 79 is getting obviously line 75 print on keyboard. There has to be some keyboard for neighbor direction. Let's see once again. I think I handled it. I can't see shit now. Oh yeah, it has to be minus in front. Huh. Look, it's done. You think it's done. You think it's done. We have achieved the normal hill climb, but let's see our init too. It has achieved it as well.